X equal to 0, so we plug in the value for inverse cosine. Well, we know from trigonometry that the cosine at pi over 2, which is 90 degree, cosine 90 degree, that is 0, because the adjacent over the hypotenuse, the adjacent approaching 0, so the 0 over the hypotenuse. The hypotenuse will stay, let's say for 1, for example, the 1 unit circle, maybe. For example, you can take the unit circle to be anything that you want, but unit circle is 1 for the length of hypotenuse. So 0 over 1, that's 0. So at pi over 2, that what happens. So inverse cosine 0 equal to c, and that is equal to pi over 2. So we know that c now is pi over 2. So now we see there's a pi involved in our series, so we see some light there. But all it is that how we managed to get this pi being formalized, in other words, it being equal to some formalization, serial formalization. Okay, so we have pi over 2 equal to that. So we have, from here we have inverse cosine of x equal to x plus x squared. Well, maybe I should write this because it says dot dot dot, right? So it's not so good to do that. Well, there's a minus sign here, so we gotta be careful with the minus sign. So if there's a minus sign here, we put the minus sign in front. This minus sign in front. It wouldn't change anything. It wouldn't change the c, but it's important to put it in. So you have cosine x here is equal to pi over 2. Because c we said is pi over 2, right? So pi over 2 minus x plus x cubed over 2 times 2 plus, I'm sorry, this is 3. Because we integrate x squared over 2, right? X squared over 2, so this here is 3. Right? And here's 5. So 2 factorial 5. Okay? Here, right? So alright? Okay. So now we have a series. Well, this series is pretty complicated. It's pretty long. But so what are we gonna do next? We're gonna simplify it and then put it in terms of what happened really when we have this equal to pi, right? So when does this equal to pi? We're gonna find the appropriate ratio value we plug in here, so that the inverse cosine of x is equal to pi, and we know that the range of inverse cosine is from 0 to pi, so it does exist, right? That the limit does exist. So how do we plug in the ratio value? Well, we know that cosine is equal to 1 when the theta is equal to 0, right? So we have this. So we have inverse cosine, we have this expansion. So we need to find, plug in the ratio value so that it's the appropriate ratio value. So when we plug in this value, going to give us pi. So we can put pi on one side, and the rest is just the formalization of the series. So we know that. So we have something like this. Let's have a coordinate, and here is 0. Pi over 2, pi, 3 pi over 2, and 2 pi. We know that cosine, inverse cosine of x equal to 0. 0 does exist because the range, we talked about this, the range does exist. the limit does exist, okay, so what the value we need to have in order to give pi? -1, right? So inverse cosine of -1 put in here, that's pi. Okay, so x is -1. So we know that therefore inverse minus 1 equal to pi. Alright? So and this pi does exist because this is in the range of inverse cosine. Alright? So we know that x is -1, so let's just put in, right, x equal to -1. Alright? Let's just put in and see what happened. Okay? When we put in, so we have inverse cosine -1 is pi, so therefore pi equal to pi over 2 minus, we put x in -1, so -1 to minus, that's a plus. So plus 1 minus, everything in here is a positive term. There's a minus in front. We put in the -1, we have an odd power, -1, with any odd power is -1. So we can minus pi over 2 on both sides. So pi minus pi over 2, that's pi over 2, this pi over 2 disappear. So we have 1, this whole series back. So we have some quite complicated series. So we can formalize or given the format of this pattern. So we can write pi over 2 equal to, let's write a format. Here we have a 1. We have a 1 plus 1 over 2 times 3 plus these. We can think of 2 here is 2 to the power of 1, and you think we can have 1 factorial here, right? Okay, and here we have 1. So, like we said before, we have in the numerator we have 1, and we have 1 times 3, 1 times 2 times 5. So we times up into that last odd number, right? So 1, let's just put the 1 aside, right? Because 1 is quite hard to include in the sigma notation, because it doesn't have any pattern that we can fit into it. But anyways, it's just estimation, right? It's not really something that we weigh that much. So we have 1 plus. It depends on where you start. Let's just say start at 0, go to infinity. Here is 1 times 3. So we may have 1 times 3 times 5 times ... 2n plus 1, right? Because we put the 1 here, so it started at this term, right? You start at this term, so 1, n equal to 0, put in here 2n, 2 times 0 plus 1, that's 1, alright? And we times up into that term, let's say n equal to 1, 2 times 1 plus 1, that's 3, and times up into that term, 1 times 3. N equal to 2, 2 times 2, that's 4, 4 plus 1, that's 5, up into 5, 1 times 3 times 2, times 5. Okay? So here we have 2 to the power, right? So first we have n equal to 1, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. So, but n starts 0. So we got a plus, right? So 2n plus 1. Alright. Now we have 3, we have 5, we have 7. Right? So it's like 1 terms ahead of this one, but it's not times up to, it's just by itself, right? Here's just 3, here's just 5, and here's just 7, right? Look at this, here's just 3, just 5, just 7. So we don't times up, we just an individual constant, so 3, you start at 3, so we're going to have 2n plus 3, right? 2n plus 3. Okay, so now let's see, we're consistent. And start at 1, that's 5, right? So 2, 4 plus 3, that's 7. Okay, so that works. That works. So now we have the factorial to be concerned about. Here we have 1 factorial, 2 factorial, 3 factorial. But n started at 0, so we can say that this times n plus 1 factorial. Okay, so this is the series where we have, but here we have pi over 2, so simply just times 2 on both sides, therefore we have pi equal to 2 plus 2 factorial n over 0 factorial 0 to infinity 1 times 3 times 5 times 2 n plus 1 over n plus 1 factorial 2 n plus 1 times 2 n plus 3. Okay? Alright. So here we have the estimation of pi, which is this series. In the previous videos, we developed a series representation of to calculate the value of pi, but it looks similar. It's shorter, but this series approaches, meaning it's more accurate. It's a more accurate estimation and approaching pi faster than if we were to use inverse tangent to estimate the value of pi. So in the next video we will talk about and discuss how do we estimate and calculate the errors, as well as comparing the accuracy between the two series that we developed for pi value. Thank you very much.